Traveling waves, aka the brain waves that travel among the different regions of the brain, are not just your decorative brainwave, so to speak. They actually provide a very powerful and very stable mechanism for maintaining working memory within the brain, even when distracting inputs are present. And so there is a way that we could discuss that the traveling waves could be key physical substrate of cognition and offer a mechanistic bridge between the biological brains with the artificial systems. And today we're going to discuss a preprint that proposes some fundamental features for real brain that can naturally emerge in artificial neural circuits when these circuits obey biological, realistic wiring constraints. Traditionally in neuroscience, we describe the brain as if it were a primarily static network of connected units passing information back and forth. For example, a neuron fires, the signal travels, computations happens, and so forth. Yet, beneath all of these familiar pictures lies a deeper organization principle that is only now becoming much more visible. The brain is not simply a network of nodes, but it is a living, moving field of activities structured by waves, aka the electrical brainwaves activities. And this preprint that I will add the link below offers compelling evidence that these waves are not decorative side effects of neural activity, but are instead a fundamental computational substrate of cognition itself. When it comes to artificial neural networks, we have achieved extraordinary performance across vision, language, reasoning tasks, and so forth, but they still lack a critical property of biological brains. Real cortical activity unfolds through richly structured spatio-temporal patterns known as the traveling waves. These waves sweep across neural tissues in organized directions and rhythms, aka the oscillations, and have been observed in sensory perception, attention, memory, decision making, and motor control, etc. But until now, most computational models of traveling waves have required hand-designed connectivity patterns and externally imposed dynamic. That approach explains what waves can do, but not how real human brains naturally produce them. But in this paper, this study addresses this gap by asking a simple but very profound question, in that under what conditions do traveling waves emerge spontaneously in neural circuits without being explicitly engineered? The answer turns out to be remarkably biological, in that when the authors built recurrent neural networks, aka RNNs, using only biological plausible constraint, including spatial organizations of neurons and directional bias in connectivity, traveling waves arose on their own. No external wave generator was required. No artificial imposition of oscillations was needed. The system organized itself into a wave-based computational regime simply by obeying the structural rules that real cortical tissues already follows. Though a key element of the model is the inclusion of an empirical neural manifold constraint, where neural activity in the brain does not explore its full mathematical space of possible firing patterns. Instead, it involves on a low-dimensional manifold shaped by anatomy, physiology, and experience. By constraining the artificial networks to operate on such a manifold, the model naturally evolved wiring patterns that support traveling waves dynamics. In other words, the geometry of neural activity itself shapes the architecture of the circuit, and the architecture of the circuit gives rise to these brainwaves electrical activities. And what makes this discovery especially powerful is that the authors here do not stop at showing that waves emerge. They actually also demonstrated that traveling waves provide a robust computational function, the maintenance of working memory, for example, in the presence of distraction. In this model, information is not stored as a static pattern of persistent firing of the neurons. Instead, it is carried and persevered by moving waves of activity that continually circulate through the network itself. When distracting visual input, for example, is introduced, these brain waves allow the memory representations to remain stable, resilient, and recoverable. The memory, in other words, does not collapse under noise. It actually rides with the waves. This dynamic mechanism of memory storage stands in stark contrast to many dominant theories in neuroscience that treat memory as a stationary attractor state. The wave-based model, on the other hand, suggests that the brain does not hold information still. It keeps information alive by actually moving it with these electrical waves. Cognition then becomes less like writing something on a chalkboard, for example, and more like keeping a flame burning by constantly feeding it energy and electrical activity. Crucially, here also the authors then test their models against real neural data, where they analyze recordings from prefrontal cortex of non-human primates performing working memory tasks and find that same wave-based mechanism at play. Neural activity in the animals here showed that traveling waves dynamics that mirror the behavior of the model itself. The same relationship between wave propagation and memory robustness appears in both systems, actually. And this convergence between theory, simulation, and biological data strongly suggests that traveling waves are not just a phenomena. They are actually a part of the brain's core computational strategy. The implication of this work reaches far beyond working memory. If traveling waves are primary mechanism by which neural circuits stabilize information, coordinate computation, and resist noise, then many aspects of cognition may be fundamentally just wave-based, brainwave-based. Attention may be guided by waves, electrical waves that sweep relevant signals into synchrony, for example. Perception may arise from interference patterns between incoming sensory waves and internally generated ones, and decision making may unfold as competing waves propagate across cortical fields, shaping which patterns actually dominate. This perspective also reframes our understanding of artificial intelligence. Most artificial neural networks operate on static activation patterns and discrete time steps. They do not possess intrinsic spatio-temporal structure. They do not allow information, for example, to physically move through the system as a wave. This may explain why current AI systems, despite their power, struggle with stability, robustness, and continual memory distraction. They compute actually without any flow. And the brain, by contrast, computes through motion. Its information is inseparable from its dynamics, so to speak. and traveling waves provide the physical medium through which thought itself moves within the brain. In this light, this paper represents more than a modeling advance to some extent. It points toward a new computational paradigm grounded in the physics of the living tissues. Intelligence is not merely the result of weighted sums and non-linearities. It is actually the result of structured movement of activity through space and through time, constrained by geometry, shaped by biology, and stabilized by the electrical waves activities within the biological living organisms. And as neuroscience continues to uncover the dynamic laws governing the neural systems, traveling waves may emerge as one of the most fundamental building blocks of cognition. The brain is not a static machine. It is actually an ocean of electrical activities and waves, and thought is written within its waves. And here is precisely where the framework of symbiotic intelligence becomes deeply relevant, where symbiotic intelligence proposes that future intelligence system will not be built solely on digital abstractions, but from tight integration between biological signals as well as the artificial computation. The traveling wave paradigm reveals that biological intelligence is inherently dynamic and analog and field-based. If artificial systems are to meaningfully merge with biological ones, they must be then designed to interface with these living wave dynamics rather than just merely sampling static outputs. The brain does not communicate its snapshots, it actually communicates the flowing patterns of activity. A symbiotic system where artificial system and biological systems meet must therefore learn to read, interpret, and participate in these type of waves. And from this perspective, traveling waves become the natural bridge between the biological cognition and the machine intelligence. They offer a physical language through which neural systems organize information over space and over time. Symbiotic intelligence envisions future AI, robotics, and humanoids that are not simply tools, but extensions of the human cognitive dynamics, co-regulating and co-evolving with the biological system. By incorporating wave-based computation and biological ground dynamics, artificial systems can then begin to operate on the same informational substrate as the brain itself. This work, for example, as concrete scientific groundbreaking for this vision by demonstrating that wave dynamics are not optional embellishments of cognition, but actually its structural foundation. Okay, folks, that's all I have for today. Thank you for watching, sharing, and liking. I'll also add some links below, not only to the paper, but also to some other books if you're interested in expanding your knowledge in this area. Thanks for watching. See you guys next week. Bye.